Good afternoon, everybody. First of all, I would like to thank Professor Patnaik and other organizers for giving this platform, for sharing my research results with you. Myself, Durga Boshak. I'm working in the Department of Physical Sciences at ICS, Indian Association for the Cultivation of Science. So today I'm going to talk about revealing the phonon dominated hot carrier dynamics in 2D van der Waal thallium gallium sulfide and its photoresponse properties. So the outline which I will follow is, first I will discuss about various charge carrier recombination dynamics, and then I'll talk about thallium gallium sulfide, how this carrier phonon interaction happens in thallium gallium sulfide, this which is chosen as a case study. And next I'll talk about temperature dependence of Raman modes, particularly LO phonon coupling strength and phonon frequency. And next, temperature dependence of optical band gap and the exciton phonon coupling. The exciton phonon coupling strength in single crystal thallium gallium sulfide as well as the exfoliated thallium gallium sulfide will be compared. And finally, I'll compare the photocarrier dynamics in case of single crystal as well as in micro flake. And of course, this will include the performance of single crystal as well as microflake. So why I am so particular about single crystal and microflake again and again I'm saying is that, in the past few one decade at least, the people are too much putting concentration on 2D transition metal chalcogenides. In 2D transition metal chalcogenides, being the layered material, many outstanding properties are found in them, and especially when they are exfoliated to few layer, even in the bilayer or monolayer, many interesting electrical, optical and optoelectronic properties are found which are of particular interest from the application point of view. So first I'll discuss about charge carrier recombination dynamics in general. There are four types of charge carrier dynamics in generally in semiconductor. One is via traps. What is it? It's the carrier recombination in semiconductor doesn't happen from band to band because the band gap is so much larger than the phonon energy. So they need a defect states in between the band gap. So here recombination occurs via the defect states. The another is the recombination assisted by the polarons. This I am going to discuss later, just finishing this. And another is the indirect band gap effect. How this indirect band gap recombination happens, due to Rashba effect or spin orbit coupling, the valence band and the conduction band is splitted. If the splitting is not similar or same, then the indirect band gap is generated, and there the phonon assisted carrier hopping happens, and then the recombination happens. And next is the photon recycling. This happens in highly crystalline substances, pure substances, where photon generated is reabsorbed and again re-emitted. So to explain more about this polaronic effect in recombination, when the light falls on a material, it is absorbed by that material and the exciton is generated, and the exciton is separated into electron hole polarons, and then this electron holes, they dissipate the thermal energy to the local phonons, and then finally they equilibrate by transmitting the energy to the lattice, and the hot carrier becomes cool. So this effect is schematically shown here, where electron polaron and hole polarons are formed here. And this formation of polarons sometimes is very beneficial because these are screened from the Coulombic attractions, and then the many outstanding electron transport property or electron extraction happens because of this electron polaron formation. So as I said, that people are putting much stress on transition metal chalcogenides, molybdenum sulfide, tungsten sulfide, molybdenum selenide, tungsten selenide, but much effort is put on post transition metal chalcogenides, where post transition means it involves thallium, gallium, etc. So I am talking about thallium gallium sulfide. It is often called ternary chalcogenide. The structure is basically monoclinic, and it is an alternate layer of GaS4 thallium, GS4 thallium, following a XMMX motif instead of XMX motif in case of binary chalcogenides. So the XRD of this particular material shows the 004, 006, 008, 0010 reflection from the sample, and using this we have found out the interlayer distance is 3.76 angstrom, and the crystal is strongly oriented along 001 direction. So the absorption spectra, fortunately the crystal was little bigger, we could manage to take the absorption spectra, which shows that there is a sharp increase in the absorption below 500, showing there is a absorption. So we have found out the band gaps, one is direct and one is indirect, and the values are written here, 2.53 and 2.49. Surprisingly, there is no much report on the band gap values of thallium gallium sulfide. Theoretically calculated band gaps show that it may be indirect band gap, some say it may be direct band gap, and some report mixed band gap type. So we have found that both band gap may exist in this material. So the Raman modes are very important, you know, it gives you the phonon dynamics, phonon details of that material. So theoretical calculations show that the GFS4 unit, the GAS4 unit, this the total vibrational mode is 4 GAS4 units are Raman active, which can give you total 31 vibrational modes. But experimentally we have found that the 4 high intensity vibrational modes, the low frequency vibrational modes are due to translational mode vibration of alternate thallium and gallium 4s4 units, and the high frequency vibrational modes are due to intramolecular vibration in the GaS4 unit. So we have matched the theoretically calculated modes with our experimental values, and accordingly we have assigned the various vibrational modes to this particular units. So in order to get deeper insight into the phonon dynamics, we have taken the Raman modes at different temperature. It shows that with decrease in temperature, there is a blue shift in the vibrational mode in all the but I need to say that we have chosen these 4 intensity peaks for this study, and there is in all 4 there is a low shift in the higher frequency as we go to the cryogenic temperature till 80 Kelvin. So there is a blue shift. So and further to this, we have seen that if one of the Raman modes, when we go to 80 Kelvin, we get different, the mode is splitted into 4, which further tells us there is a change in phase. So this fixed shift is fitted with a linear equation. This is omega equal to omega 0 chi t. Simply the temperature effect is considered, and we have found that different chi values, and also we have fitted this variation with Balkan's equation, where the A is particularly inserted. What is A? This is anharmonic constant. For this type of compounds, the anharmonicity is very important to consider. This gives you the idea of phonon-phonon interaction. So introducing this anharmonicity constant A, the Balkansi proposed this equation, and we have fitted this data with this equation also and found out the value of A. And we have found out the value of B, another anharmonic constant, where the 3-phonon interaction is considered following the FWHM plot as a function of temperature for all the 4 intense Raman modes. And we see the phonon mode softening as we increase the temperature. Means less interaction as we increase the, more interaction as we increase the temperature with the phonons. So we have calculated the value of B also, and as a function of Raman frequency, when you see the anharmonic constant for the higher frequency peaks are quite high, and these are responsible for out of plane vibration of sulfur in that material. So this was all about single crystal thallium gallium sulfide. Why, and you must note that the constants are this, and when we go to microflake of 82 nanometer after exfoliation, we see the values become much less. Here I have given this table where I have compared the values of chi A, B with those of single crystal. You see all the anharmonic constants are lesser in case of microflakes. So from this result we can say that smaller anharmonic constant and weaker phonon coupling broadening happens in microcrystals. And so this diminished lattice anharmonicity tells us that the phonon decay is different in when we go to microflake. So let's see now how the band gap changes with temperature, and that tell you about exciton phonon interaction, of course. And here I have shown you that is a photocurrent spectroscopy as a function of energy, and we see that as we decrease the temperature up to 11K, this excitonic peak becomes very strong, and from these excitonic peaks for all temperatures, using the lambda half method, we have calculated the band gap of this material, and we have found that it follows a curve like this. Up to a certain temperature, there is no much change in the band gap, but after that the band gap falls rapidly. But in case of microflake, you see there is no change in band gap, almost invariant of temperature. So you know how band gap changes with temperature. When the temperature increase, the volume increase, of course, and this should give you a blue shift in the band gap. The first term is responsible for blue shift, and this term with the phonon interaction, which should give you red shift. So this is the phonon occupancy following the Bolt and Einstein distribution law. And so this curve we have fitted with O'Donnell and chain model following this equation, and from there S, the dimensionless exciton phonon coupling constant for this material has been found as 4.42. Okay, so you can compare with MoS2 and indium selenite, which are quite lesser than this value. Next, we have compared the photoluminescence of this material as a function of temperature, and we have deconvoluted this broad peak into 2 peak at room temperature, which is termed as A1 and A2. But when we go to lower temperature, another peak arises, which is due to bound exciton XB. Okay, and if the temperature is further decreased at 80 Kelvin, this peak becomes intense and comparable to this A1 and A2. So we have found the FWHM of this bound excitonic peak at all the temperatures and fitted following this equation. Okay, and this gamma yellow is giving you the coupling strength of exciton with yellow phonons. Okay, the acoustic phonon doesn't interact much, but the yellow phonons interaction is more with the excitons. And this gamma yellow is found to be 849 millielectron volt, which is quite high. But if you compare with the other values in other compounds, bound excitons, the gamma yellow is generally these are the values. Okay, so this particular ternary chalcogenide, the exciton phonon coupling strength is quite high. From this value you can see. And another is frolic coupling constant is very important, alpha. You know, when the polarine is formed, there is a decrease in the potential, and this is given by this equation, and the alpha is the frolic coupling constant, which gives you the how the yellow phonon interact with the exciton. So this gamma yellow is found to be 80, gamma yellow is 0.8. Okay, so it is also quite high for MOS2. Sometimes it is found around 1, 1.2. Various values have been reported for MOS2, WS2. So naturally, when this interaction is more, phonon exciton interaction is more in some compound, we should expect longer carrier lifetime in that case. And indeed, we have found that in single crystal, the carrier lifetime is 1.02, whereas in case of microflake, the carrier lifetime is almost half of that value, 0.55. So the hot carrier relaxation path in case of single crystal and in case of microflakes are quite different. So in order to know more about carrier phonon interaction, we have formed photodetector devices on single crystal, and this is on the microflake. So in the single crystal, it was about 194 micron, and the microflake, the AFM image shows that the thickness of the microflake is almost 80 nanometer. So this photocurrent spectroscopy is very important. It tells you a lot of things about this recombinations or the electron hole separation. For the single crystal, we get a sharp peak at around 490, and as we decrease the wavelength, that means increase the excitation energy, then the photocurrent decreases, and this decrease is due to the surface recombination. But whereas in case of microflake, as we decrease the wavelength, that is increase the excitation energy, you don't find any decrease. More or less the photocurrent remains the same. So we have studied this experiment at different temperature, and this is the contour plot, where this says that as we decrease the temperature, we get a sharp peak, but there is always a shoulder which is which is in the range of 500 to 400. But in case of microflakes, we get a sharp peak, and we get sharp, there is no change in the photocurrent. So we say the weaker photocarrier phonon coupling happens here, whereas strong photocarrier phonon coupling happens in case of single crystal. So we have done photocurrent transient experiments where we have illuminated the samples with light of 405 nanometer with power 120 milliwatt per centimeter square, and we have did this experiment at different temperatures. We have found the maximum photocurrent and plotted as a function of temperature, and this gives a very interesting plot, because you see up to a certain temperature the photocurrent, when we cool the sample up to a certain temperature, photocurrent remains same, but below that photocurrent sharply increases. So it means that below certain temperature the interaction is less, so it gives rise to high photocurrent. But in case of microflake, the photocurrent remains almost temperature invariant in the temperature range what we studied. So This again is in line with the Raman experiment or the photoluminescence experiment, that strong carrier phonon interaction happens in this crystal, but in case of microflake it is less. And this particular slide shows you the photo response and photocurrent transient of single crystal. And the single crystal is responsive to all the wavelengths, 650 nanometer, 532 nanometer, 405 nanometer. As you see, as soon as the crystal is shined with 650 nanometer light, the current increases, and when we switch off, the current decreases. It happens same in case of 532 and 405 nanometer. That means it has in gaps, sub-band gap defects in the caused by the sulfur vacancy. And these are the cycles showing the stability and the response speed of single crystal device. And from here we have measured the time of response and decay, which are 50 millisecond and 145 millisecond, and the frequency modulated response of this single crystal in the time domain is like this. And from there we have found out the -3 dB frequency value is 8 Hz in case of single crystal. We know that in case of photocurrent, it follows this I photocurrent proportional to p to the power half. This is power, p to the power alpha. Alpha is the parameter which defines how the carriers are separated. If alpha is 1, it is good, the electron holes are quickly separated. But if alpha is less than unity, then there is a trapping. So here we have plotted power density versus photocurrent, which says that at low power the alpha is 0.4, whereas at higher power it is 0.52, and for all the wavelengths it is, for lower power the alpha is much less than unity, but higher power it is somehow near to unity. So in case of microflake, we have done similar experiment. The microflake is also equally responsive to 405 and 532, but surprisingly it doesn't show any response to 650 nanometer. So it shows a rapid rise in the photocurrent for 532 nanometer and of course for 405 nanometer. Again we have plotted here power density versus photocurrent, which show alpha value better than the single crystal. If you remember, it was around 0.8 and it is now almost 0.88, means it is much nearer to unit value. So here we have compared different photo response parameters, and if you look at this table, you can see that the responsivity, detectivity, response time, in all respect the microflake is better. So the better properties in microflakes is probably due to the lesser electron phonon or exciton phonon interaction in microflakes because of dielectric screening. So I must acknowledge the funding agency. Initially it was SCRB and then ANRF, CSR, and of course my institute, ISCS. And I also acknowledge the work done by my students. Thank you. Thank you all.
Were there any questions?
Can you hear me?
Yeah.
So my question is, why do you think this enharmonic phonon-phonon coupling is so different in your silicon crystal, the single crystal and microflake?
Yeah, I said already that enharmonic constant, it depends on the many factors like strain, environment, etc. So in single crystal, the environment is bit different. I'm not saying that it is quite different, a bit different compared to the microflakes, because it is known that if you thin down these layered materials, you get more dielectric screening. So that probably gives the less enharmonic constant.
Micron size, so
Yeah,
it
yes.
shouldn't have too much difference compared to the.
Yeah, not it is micron, it is nanometer.
Oh, it is nano.
Yes,
Okay.
less than 100
Okay, you
nanometer.
are calling it microflake, but you are saying
Microflake in terms of length.
Okay.
Thickness is 80 nanometer. I have shown already. Mhm.
Thank you.
And the problem is with this ternary chalcogenides is that thinning down to lesser than 50, 60 nanometer is very difficult, unlike dichalcogenides. So we could not exfoliate less than 80 nanometer. It was not successful.
It was a nice talk. Ma'am, I have one question that why there is a discontinuity in the power law fitting, I mean the low power and high power.
Yeah, that's a good question because it was not the same source we used. Actually, the source was different. The excitation source was
I have a
different.
system where using the same source also there is a discontinuity in the low power and high power system. So what can be that reason? Can you
Here in my
there are systems where if they are gradually increasing also low power, high power,
yeah.
but there are two type of fitting curve will come.
Yeah, of course, the higher power should be able to extract more carriers, right? More separation of electron holes, right? More generation and separation. But photo getting generally happens when you increase power more and more. But in this case, I don't know which case you are talking about. In this case, we have not found any photo getting effect, rather photo conducting effect.
I am also talking about some TMTs only,
Huh.
dichalcogenides.
Yes.
In that system also, they are just saying about due to transcripts like this is happening, but they are not saying any proper reason why there is a discontinuity. Directly, it will jump to a different. Uh,
Yeah.
So yeah. Okay, ma'am. Thank you.
Because there is a change in slope, na. For lower power, the slope is different, and the higher power slope is different. So there should be. But in my case, the discontinuity is because I could not find any source with all the powers, excitation powers.
So, are there any more questions?
Yeah, very nice presentation. This thallium gallium sulfide, you are showing about the nature of the band gap.
Yes.
So, one is the direct, you said, and there is an indirect.
Yeah.
So, can it not be a single gap also? Like, how do we, how does that, because you are just plotting it in, like, as an
and
analysis of the direct and indirect.
yes.
Is it possible to also have just one of them? Like,
Yeah, that's what I told, that there are very few reports on band gaps, and it was mostly theoretical calculations. Some say it has direct band gap, some say it has indirect band gap, but some theoretical studies have found that they are having both direct and indirect. But you know, the one of the beauty for this transition metal chalcogena is that when it is in bulk form, it shows indirect band gap, but when we go to bilayer or monolayer, it becomes direct band gap, and that is the beauty of transition metal chalcogena, is why people are doing this.
So, if there are no many questions, just thank the speaker again.
Thank you.